Hello and good morning to all of you for attending such an important training on NFPA 70E. In today's session, we are going to discuss a very important Article 130 and its important clause 130.5 arc flash assessments important subpart that is 130.5G arc flash risk assessment. Before going to start today's session, I would like to introduce myself. My name is Rais Malik and I am an electrical engineer. I got top position in my university with a medal and the certificate of achievement. I have 14 years of comprehensive experience in electrical maintenance and reliability, asset integrity, electrical projects, electrical planning, and also perform my duties as SAP planner. I also got served in top rated companies in Pakistan such as Fuji Fertilizer, Prime Global Energies, Sindh Agro Coal Mining Company, National Refinery, and recently working in ENI Pakistan, that is Bhit and Badra gas field. I have achieved 150 trainings and certifications in electrical systems, that is power, control, automation, electrical safety management, project management, maintenance management, budgeting, electrical safety analysis, and other safety as well as soft skills. I am also an approved NFPA 70E trainer and also a lead auditor of ISO 45001. In the last year, during my services in ENI Pakistan, I won HSE Leader Award for the best stop program observation, and also got a Safety Slogan Award at Fuji Fertilizer in 2017. That's all about my brief introduction. Now, on today's session, what we are going to learn, that is incident energy analysis. So we are going to discuss what is an incident energy, then factors on which incident energy depends, then we are going to calculate or we are going to discuss arc flash boundary and calculate incident energy. Then based on calculated incident energy, we are going to discuss how we can select PPE for arc flash hazards. Then we are going to develop and design the equipment labeling based on incident energy. And then in the last, we are going to discuss the engineering controls and their impacts on incident energy and how we are going to reduce the incident energy by using engineering controls. And then in the last, we will going to summarize the key takeaways and the lesson learned in our session. So let's start incident energy analysis. Incident energy analysis and PP selection is very important topic in the article 130.5, that is arc flash risk assessment. So NFPA 70E 2024 standard describes how we can calculate incident energy based on IEEE 1584 standard. Well, what is an incident energy? As per the definitions of NFPA 70E, incident energy is the thermal energy from an arc flash that reaches a worker at a specified distance. It's not total explosion energy, it is exposure density. The incident energy is denoted and measured in calories per centimeter square and sometimes in joule per centimeter square. The incident energy is basically going to calculate for low voltage on a distance of worker from the equipment, that is 18-inch, or we can say 455 millimeter. NFPA 70E uses incident energy to select PPEs. How we going to save employees when any employee is working on a live equipment that persists or that has the capacity of arc flash hazard. And due to that arc flash hazard, the incident energy is going to arise and can damage to the health or of the employer. So this is the very important and basic method to calculate and to select the PPs based on this calculation. Now, what are the important parameters on which incident energy certainly depends? So according to IEEE 1584 method, 7 parameters are required. Number 1 is system voltage. Number 2 is how the LV switchgear is designed. It is metal clad switchgear, it is or any other type of the switchgear, that depends on the design factor. And the third one is available voltage fault current. And the fourth one is the gap between the three-phase conductors on which the person will going to work on a live equipment. And the fifth is the grounding system, how the system is grounded. It is either solidly grounded or grounded by a resistor or reactance or any other type of grounding. And the working distance between the live equipment and the person, that is 18 inch or maybe 12 inch, or depends on the situation, either 24 or 36 inch. And the seventh and the most crucial and important factor is arc duration, the time required by the relay to clear the fault. That we call is arc duration or clearance time. So incident energy is basically dependent on some of the main factors, that is 4 are the manipulated variables or the important variables on which it depends. Number 1, that is on arc power, that is the multiplier of voltage and the current magnitude. Number 2, duration, the time the arc persists before protection trips. And the number 3 is the square of the distance between live equipment on which the person works and its distance between both of them. So other factor is the enclosure factor, where the energy is focused or allowed to escape during arc flash. So incident energy analysis increases as long as the arc is stronger and it lasts stronger. And it also depends how closer is the person working on the equipment, or it also depends on the design of the equipment. So these are the very important factors, are the very important factors on which incident energy depends. Now we are going to discuss each parameter, that is working distance. So it tells us that if we double the working distance, the incident energy reduces by 75%. Let's see in the picture, when we have a distance of 12 inch, the incident energy is all about, we can say that 18 calories per centimeter square. That is extremely dangerous. When we move further from the live equipment, then on 18 inch the incident energy is 8.5 calories per centimeter square. Then if we going to increase the distance twice, then at 36 inch the incident energy reduces to 2.5 calories per centimeter square. So what is the working distance? As we already discussed, the distance from the arc source to the worker's face or chest. As a matter of fact, the energy spreads out like heat from a fire. That is inverse square law. Small increases in the distance yields a massive safety dividends. How are we going to explain that? If we move away from the live equipment on which the person is working, the incident energy is drastically reduced. That is, the physical examples is that when remote braking or long insulated tools is used, then it plays a very critical life-saving technologies, because it reduces the distance. So subsequently the arc or incident energy is reduced. So the other parameter is fault current. The maximum fault current does not always equal maximum danger. So look at in the graph. The graph is very clear. Look at the point at 10 kiloampere. the amount of clearing the time is 0.6 seconds. So the incident energy is 6 calories per centimeter square. But look at that, the current, when the current in the curve is 50 kiloampere instant trip, and the time for the clearance of the fault is 0.05 seconds, then the incident energy is about 4 calories per centimeter square. When look at the peak point, that is 25 kiloampere, that is the peak of the curve. At that point, the current is 25 kiloampere, but the clearance time is 0.4 seconds. So it is a dangerous zone, and the incident energy increases as 14 calories per centimeter square. So it is clear that as long as the fault current increases, and the relay operating time will remain constant, the incident energy always increases. But if we are going to increase the current as the tripping time or the clearance time decreases proportionally, then there is will be no impact on the incident energy. So if current is going to increase, the incident energy is increasing depending on the clearance time of the relay. So this is very important parameter. Now the other important parameter is the conductor's gap. Look at the picture. When there is a gap in the conductor is about 25 millimeter, there is a small gap. The arc is stable, and it takes longer duration to clear the fault or to clear the arc flash. That is, the incident energy is 15 calories per centimeter square when there is a distance of 25 mm between the conductors. When it comes to the larger distance between the electrodes or conductors, that is 100 millimeter, that is MV switchgear, then the arc remains unstable because there is a large gap, so arc cannot restrike or persist. So at 100 millimeters of gap, the incident energy is about 7 calories per centimeter square. That is quite lower than the distance at 25 millimeter. So it is a very important parameter, and that's why the IEEE 1584 models gave width as a primary variable. Now, in order to determine the incident energy, we are going to find some very important parameters, and we are going to calculate it. The number one is voltage fault current. This is the maximum potential current that flows during a fault condition. Like that, a voltage fault current is 25 kiloampere. And the main point that we are going to focus is arcing current. The arcing current is the actual current that is flowing through an arc. And the arcing current is always lower than the voltage fault current because of an arc resistance, of the resistance that creates during an arc. And the other important parameter is protecting clearance time, the time required by the relay to clear the fault, and the time is 0.20 seconds. That is the duration determined by the Bragg trip curve, or it is very important for calculating the incident energy. In the step 3, we are going to calculate incident energy. There is the current multiplied by the time. There is by applying the IEEE equation, that is standard 1584. So how we gonna calculate incident energy is based on these two parameters. That is the incident energy comes out as 6.5 calories per centimeter square. In the fourth step, after going to have an incident energy of the equipment upon which the person is going to work, we have to define the arc flash boundary. That is, this is the equipment, and this is the total distance from the equipment, and the boundary distance is 4.6 feet that we have defined. And this is the incident energy circle, and the incident energy is 6.5 calories per centimeter square, and the working distance upon which the person is working on live equipment is 18 inch. So this is the region where where and when the person or the electrical technician will going to work, have to wear and selected the arc flash PPEs. Outside this important region, the person is declared to be safe and is outside the region of hazardous electrical or arc flash energy. So the fundamental relationship is on incident energy, that it depends on arcing current as well as arc duration. So the main parameter is the arc duration, and the time is the dominant variable. It is the lever we can control. So by controlling the time of the relay to clear the fault, we can reduce the incident energy. So this the histogram or the graph shows how the incident energy will going to be reduced by reducing the time of the delay or fault clearance time. So look at that, at 0.50 second on the red, the incident energy is 12 calories per centimeter square, and when we reduce the time to 0.25 second, the incident energy will going to reduce to 6 calories per centimeter square. So when it will reduce 0.10 second, then the incident energy will going to reduce 2.4 calories per centimeter square. So this picture will tell you, is going to tell you that by reducing the time of the relay or the arc or the fault clearance time, we can reduce the incident energy significantly. Now we are going to discuss the engineering control to reduce the incident energy hazard. There are many methods that are used to reduce the incident energy and the duration of the arc, so that it will not persist longer and cannot damage the employee working on any live equipment. So number one is zone selective interlocking. So there are intelligent communication between breakers for fast tripping. When there is a fault or there is an arc flash or there is a huge incident energy arises, then it trips the system more faster than the conventional system through zone selective interlocking. The second method is the ERMS, that is the energy reducing maintenance switch. What it will do, it will provide protection on the equipment during its operation, and when we are going to do any maintenance on the system, we are selecting the switch to maintenance mode. So what it will do, it will reduce the tripping time or the fault clearing time during the maintenance mode. So there is a significantly reduce in the incident energy from the normal operation mode to the maintenance mode. So the employee will be safe and there will be no significant harm to the employee during an arc flash or during an arc flash hazard. The third method is the arc flash relay. So there is a optical detection relay. When there will be any type of fault or arc flash, it detects the situation of the arc and triggers instantly the device or the relay, so that the fault is cleared on an instantaneous basis. The fourth one is the differential relay. In this method, a very speed and very highly speed differential relay or differential current relay is used to clear the fault. So when we are going to discuss the engineering controls, there are the tools such as the remote racking. Through remote racking, we are going to increase the distance and the geometric difference between the live equipment and the person, so that the arc flash occurs cannot or will not do any damage to the employees or reduce the intensity of the arc flash. And the second one is the maintenance mode. As already discussed, in maintenance mode, the incident energy is reduced significantly by reducing the time of the relay to trip the circuit during the condition of voltage fault or arc hazard. So the third one is the current limiting fuses. Such type of fuses are used to reduce the peak energy or the magnitude of the current that causes the fault to sustain and to be more stronger. So by limiting the current, we can reduce the incident energy. The fourth one is the arc resistance gear. That is the enclosure specially designed or made to capture the arc during an arc flash hazard. So it reduces the impact of arc flash on any employee working on the live equipment. So number fifth point is the better relay setting. By making a better relay and the coordination of the relay, we can reduce the incident energy significantly. So these are the techniques that are used to reduce the incident energy. Thereby, the damage to the person working on a live equipment will be reduced significantly. So we are going to discuss one of the mode that is maintenance mode. In maintenance mode, we are using energy reduction maintenance switch. As per recognized by NFPA 70E clause 130.5G and NEC 240.87. In maintenance mode of energy reduction maintenance switch, the goal is to clear the fault in between 0.03 to 0.08 seconds. The main purpose of this maintenance mode and energy reduction maintenance switch is to sacrifice the system reliability but to consider human safety, so that during any maintenance activity on live equipment, the safety of the employee is to be on priority, so that it will not hurt to the employee during working on the live equipment. So the picture clearly shows the difference between the maintenance mode and the normal operation mode. So this is the physics of the switch. This is the curve that shows the difference between the normal mode and the maintenance mode. So you can clearly see on the graph that on the orange curve is the normal mode, and the blue curve is the maintenance mode, and it clearly shows the significant reduction in the incident energy. So if we can summarize it, the normal mode protects the equipment, that is coordinated, and the maintenance mode protects the human, that is the priority is to save the human during any unforeseen situation or arc flash hazard. So this is the case study and the difference in seconds. When we are going to compare, the left side is the worker no switch. When there is a normal operation and the time to clear the fault is 0.5 seconds, then the incident energy is around 20 plus calories per centimeter square. That is very large, and it will cause a severe burns to the employee working on live equipment. And if he will or is selecting the PPE of around 8 calories per centimeter square, then it is not enough to protect the employee. On the right side, the worker B with switch having arc clearance time is 0.06 seconds. So the incident energy on the maintenance mode is less than 3 calories per centimeter square. And if the person is going to wear or selecting the PP of around 8 calories per centimeter square, then if any unforeseen situation occurs or arc flashes occurs, then the incident energy is reduced significantly, so the employer will be safe. So PPE limits injury, maintenance mode prevents the energy from reaching the significant level, so it protects the employee. So there is also a summarized table in such that when there is a duration of 0.45 seconds, the incident energy is at 18 calories per centimeter square. Then it will clearly cause fatal burns. And when there is a maintenance mode and the duration is 0.06 seconds, then the incident energy is around 2.1 calories per centimeter square. That is a survivable if any thing or any unforced situation is going to occur. So on the same panel, on the same equipment, on the same fault current, if we are going to reduce the time, we will reduce the 90% energy or the incident energy. So it is very important to select or to minimize the time of the relay, so that the fault will be clear as soon as possible. So on the summary and the key takeaway, the equation is going to be energy is equal to heat intensity in the and multiplied by the duration. And the very key factor and the enemy of the system is or the fault condition is the time. The time is the killer. The solution is the maintenance mode, and on maintenance mode we can reduce the incident energy by selecting proper PPEs, and on maintenance mode we can give a survival, or we can provide a survival mode to the employee. If energized work is unavoidable, maintenance mode is not optional, it is the survival mode. So survival is determined before you open the panel. Always follow the protocol, reduce the time, eliminate the hazard. So further, on the basis of the incident energy, we will going to calculate and we will going to select the PPs based on the table 130.5G, that is the selecting the PP based on incident energy method. So for 1.2 to 4 calories per centimeter square, we will going to select the PPs, arc rated shirts and pants, and for 4 to 8 calories per centimeter square, we will going to select arc rated shirt plus pant plus face shield. And for 8 to 25 calories per centimeter square, we will going to select arc rated flash suit. And for greater than 25 or 40, we will going to select arc flash hood suit. And for that, or along with that, we will select other PPs necessary to protect all the hazards during any arc flash situation. So the equipment level, that is also selected based on the incident energy. So according to the warning or the label, there is written an arc flash or an shock hazards. Appropriate PP is mentioned on the label. Incident energy, that is 6.5 calories per centimeter square at a working distance of 18 inches, and the arc flash boundary, that is 1 feet 5 inch, and the PP rating, that is 8 calories per centimeter square. The shock hazard, that is 480 volt AC. This is the system voltage, and the equipment name is the main switchgear 1. The label must be applied to the equipment to communicate the specific hazards to the employee working on any or near the live equipment or the trained personnel. So when it compares to the comparison between engineering control and the PPE based on ISO 31000 and scenario standard protection, when there is a clearing time of 0.30 second, the incident energy is 11 calories per centimeter square. And when there we will use energy reduction maintenance switch, then when there is a clearance time of 0.08 second, the incident energy is will going to reduce 3.2 calories per centimeter square. So reducing clearing time improves mobility and safety. And the engineering control is the best solution because it eliminates or reduces the incident energy and the source. So based on ISO 31000, the best and the most important hierarchy of control is the design and engineering. This is the third control. So when we apply it, so we are going to reduce the source or the hazard and eliminate that source. But in the in the last line of defense is the PPE. If we are not going to able to if we are not able to do any design or engineering, or we cannot reduce through design and engineering technique, then the last line of defense we apply is PPE, so that the employee will going to be or will be safe in any unforeseen situation. So design plus distance plus speed prevents burns. So what are the key takeaways and from this session? The key takeaways are that PP rating must always be greater than the calculated incident energy. And the second one is the clearing time is the most effective lever to reduce hazard levels, as already we have discussed. Higher fault current does not always mean higher energy. Be aware of the blind spot. Sometimes higher fault current persists with the higher energy, but sometimes it cannot be. So always focus on arc duration or arc clearance times or the fault clear times of the relay. And the fourth one is always evaluate between maximum and minimum arcing currents of the system. And always prioritize engineering control, reducing time over increasing PP weight. So always prioritize engineering control so that we can eliminate the source or the hazard rather than relying on a PPE. So that's it from today's session. Goodbye and have a nice day. Thank you.